Welcome to this webinar about traffic modeling use case and its optimization with EVEREST technologies. I'm Radim Cmar from Sygic, and I want to present our traffic ecosystem, its functionality, its challenges, and methodology of converting it into more performant application using technologies of the EVEREST project. For a start, let me introduce the EVEREST project. EVEREST stands for Design Environment that simplifies the programmability of high-performance big data-oriented applications such as traffic modeling, which comprises of several challenging computational kernels revolving around machine learning and operating on big data. The focus of EVEREST is on applications which can profit from heterogeneity, reconfigurability, distributed approach, scalability, and require security. Let me give you the outline of my presentation. First, I want to introduce the Sygic traffic modeling ecosystem for smart mobility. Then I will go deeper into describing its functions, architecture, data, and computations. In the next, I want to stipulate the application goals and challenges, which are typically about improving the performance and energy saving. And then in the end, I want to showcase the EVEREST Optimisation technology and show the results we achieve with that. Let me give the high-level picture of our traffic modeling ecosystem, which is focused on cities. So why are we dealing with it? It's because the traffic is still a problem. Urban traffic still is on the rise. There's a prediction 75% of population will live in cities in 2030, and it will even grow. City congestion has significant costs on the economy and accounts for 40% of CO2 emissions in cities. So if city wants to improve the traffic, it needs some clever tools which provides them with analytics and predictions, so to understand what is going on their road network. Our ecosystem forms the product which ingests various data from road sensors, from cars, in terms of the GPS positions, possibly SIM cards, and provides outputs for analysts and planners, as well as functions for drivers. More concretely, our product contains computation of traffic view, a traffic analysis tool. Well, that's the functionality of what-if analysis, so city can investigate what will be the traffic state if, for example, road closes or tunnel closes. Then we provide a prediction service on a full road network, both short-term prediction and long-term prediction. And last but not least, routing service with some collaborative intelligence for drivers. From the technology perspective, it inherently works with big data, especially data we are collecting from moving vehicles, which goes up to the terabytes if we are talking about collection of data over a couple of days. And we exploit AI functions such as neural network, Markov model, or probabilistic routing. From the business perspective, with EVEREST, Sygic is extending its mobility services with new functions as well as improving existing ones. Concretely, traffic prediction, what-if analysis, and intelligent routing. Traffic prediction is to visualize the current traffic state on the road network of the city, as well as to see prediction 5 minutes, 10 minutes, 15 minutes, 1 hour ahead of time. What-if analysis is the tool which allows us to see what if scenarios. So what would be the traffic state if at current conditions there would be a close of an important bridge, how the traffic would move and how it change in a city. Then the intelligent routing is a service for our drivers, through which we are providing drivers with alternative routes such that they balance the load of the road network. Data flowing into the system are car data from vehicles collected through Sygic navigation application. So the data we call floating car data, and they represent GPS positions associated with speed information, which are collected from the car sensors through the Sygic navigation application. So for the drivers who are using Sygic navigation, we collected these data approximately 1 data per 30 seconds. And another data are from external sources, such as origin destination matrix or road sensors. Origin destination matrix are the data which define the mobility across cells in the city, so in a kind of network grid. And these data are typically possessed by mobile operators. So to achieve our product goal, to improve our services, we are in need of a performant infrastructure, which comes with Everest both in terms of a platform, such as those provided by IBM and IT4I as supercomputing center, and optimization tools, which are coming from our technological partners, such as TUD Dresden, IBM Zurich, and Politecnico di Milano. These tools allow us to accelerate key processing components of our systems, such as FCD processing, traffic prediction, traffic simulator, and routing service. Looking inside our traffic ecosystem, there are several major computations, as mentioned previously. All of them are operating on big data and use some AI techniques. The major input data are floating car data. So these are the GPS positions associated with speed information collected from Sygic navigation. Origin destination matrix, the mobility information from telecom operators. And of course, the road network represented by a map. With the simulator in the loop, the simulator is this critical component of our system. So the simulator, acting as a digital twin, allows us to generate a lot of data to learn traffic patterns. And this learning of traffic patterns we are storing into our neural network model. As well as our computation system generates direct output, such as traffic view and speed profiles. Speed profiles are the kind of long-term traffic prediction, which gives you the information what will be the speed of a particular road segment at 7 a.m., 8 a.m., 8:30. So at whatever time instance across the whole week. And then there is an extra output, which is the 3D traffic model, which associate extra information on the road segments, such as the information on the density, means how many cars are at a particular time instance on the road segment, as well as the flow. So what's the flow of the cars? What's the intensity passing through the road segment? And there is extra traffic services as an output of our platform, which are meant for third-party applications or Sygic navigation or whatever navigation, such as the traffic prediction and intelligent routing. I want to demonstrate improvements of 3 subsystems of our traffic platform being defined as workflows in the terminology of EVEREST methodology. So, meaning that we will use EVEREST techniques to improve the performance of processing of those workflows in terms of the speed, energy saving, and scalability. So here we are talking about 3 workflows: FCD processor, prediction service, and traffic simulator. The first workflow is the FCD processor, which takes as an input FCD data and the map data and generates road speed profiles. So the key component of the FCD processor is the map matching, which takes a sequence of noisy GPS sequence and tries to derive the speeds on that small trajectory of the vehicle. There are subcomponents within this map matching component, such as GPS projection, Viterbi, trellis, and interpolator, which are good candidates for acceleration. Another workflow is the traffic prediction service, which takes as an input a neural network which has been learned from training sequences. And the neural network structure itself is a good candidate for acceleration. For the third workflow, which is the traffic simulator. Traffic simulator is the main component here, which uses some routing subcomponent where there is this functionality of so-called probabilistic time-dependent routing, which is the component which is a candidate for acceleration. Traffic simulator, as was mentioned, takes an origin destination matrix as an input, along with speed profiles on the road network. It generates 3D model and training sequences. Let me visualize the functionality of the 3 computations through outputs. First, there is this FCD processor, which generates traffic view and the speed profiles. Here, the speed profiles are shown on 24 hours a day scale for many roads. And as you might see, as you might recognize, there is this pattern that the speed decreases at peak hours, that is 8 in the morning and 4 p.m. afternoon. In neural network prediction workflow, I would like to point out that we are learning thousands of neural network models across the whole city. And one prediction is basically the execution of all those thousands of neural network models at once, such that we obtain all roads, all speeds on all roads across the city at once. There is this traffic simulator workflow, which takes as an input origin destination matrix and speed profiles, and generates rich data from simulation which mimics actual or theoretical city conditions. So let me run this video to demonstrate the traffic as it evolves over a couple of hours. As you can see, the color on roads representing the speed information dynamically changes over the run. And as the simulation runs, it generates all those training sequences from which we can learn traffic patterns. Let me now take the view on the components or workflows in terms of the initial performance status and optimization objectives we stipulated at the start of the project. And I will also give a sneak preview on the final achievements. So for the FCD processor, which executes which 1 day of data collection is approximately 20 million samples. The execution took originally around 12 hours on a regular CPU. Well, we stipulated the objective to have a 5 times speed up and energy saving of 50%. What we achieved with using EVEREST optimization was the speed up of 30x and energy saving 75%. With traffic prediction, which is about for a small city which has a 10,000 models, and we need to execute 10,000 predictions. On a regular CPU architecture, it took 6 seconds. Since this is a real-time service, we want it to be a sub-second. Here we achieved the speed up 24x, while we stipulated speed up 5x. And as well as we got a better energy saving as we originally planned. With Traffic Simulator, we wanted to increase the scalability of the solution. So Traffic Simulator at the start of the project was able to execute in parallel 50,000 vehicles, while now it can execute more than 250,000 vehicles. And the simulation time speed up was supposed to be improved by 3x, and we reached that goal. Let me now explain the EVEREST optimization with Traffic Simulator with a kind of user story. There is this fkit tool, which is developed within EVEREST, used as a library, which allows distribution of a selected function, call it a kernel, into multiple nodes and workers on HPC architectures. So first, kernel needs to be modified to comply with 0MQ data interface. Then the simulator binds the kernel with fkit through its interface, defining parallelizing requirements. And at the simulator start, fkit will automatically distribute kernel and manages data exchange over the whole run. So the original architecture with a single ptdr kernel instance will translate into the following scheme, where the kernel is multiplied across nodes and workers. For those who want to use the simulator, the user interface requires as an input location rectangle, like defining the city in which we want to execute a simulation, like for example Prague. We need to input the origin destination matrix, which actually defines the number of cars which will be used in simulator, and it needs to define the number of nodes and workers and launch the simulation. Let me present the results in the table. Here you can see that the baseline using just a single kernel instance that is without fkit took approximately 3,600 seconds. And as we are increasing the number of nodes using the fkit and increasing the number of nodes and workers per node, we are reducing the computation time up to more than around 1,000 seconds, which ultimately brings us the speed up over 3x. Let me now outline the FPGA acceleration methodology and technology developed within EVEREST. The user story is that user can annotate a function, we call it kernel, of his C++ or Python code as to be uploaded to FPGA. Then with several hints from user, such as parallelization degree, fixed point definition for floating point operations, EVEREST compilation flow takes over and generates hybrid architecture executable. With EVEREST, we support two FPGA flows. One is for bus-attached FPGA architectures, and another flow is for cloud FPGA architectures. In bus-attached architecture option, EVEREST compilation outputs executable which takes care of FPGA management completely. It means it makes sure that at the start of the application, FPGA bit stream is deployed on FPGA resources, and this particular kernel is offloaded to FPGA and executed as such during the run, while the rest of the system is running in CPU space. The example is the FCD processor. Here we have this one in C++ design, and we can offload the components such as GPS projection, Viterbi, trellis, interpolator. In the cloud FPGA option, EVEREST tooling deploys defined function on cloud FPGA with generated socket interface. Example here is our prediction service, which is Python, TensorFlow, or PyTorch design. And here we are offloading neural network kernel on FPGA cloud. Let me still go deeper into showing the EVEREST optimization with the FCD processor. In the original C++ code, we can annotate the functions to be offloaded to FPGA with a pragma syntax. Then we use command line interface of EVEREST compilation, here a bit simplified, which is given the architecture information and which will do the job. It will understand that it needs to call FPGA compilation path for annotated kernels and leave other code to GCC compiler and bind all things together, resulting in executable which exploits heterogeneous architecture. So finally, the architecture may come out like this, where some functions are in CPU space, like trellis and interpolator, while others are offloaded to FPGA for acceleration. Some results here. The original code was running for approximately 12 hours for 1 million vectors. As we offloaded the GPS projection into FPGA space, we came already to 47 minutes. And when using the parallelizing option by instantiating 8 instances of the kernel, we got to 29 minutes. Even we were able to do the hybrid GPS projection architecture option where few instances were in CPU while 8 instances kept in FPGA. And with this rather sophisticated architecture option, we got into the speed up of 30x. And finally, let me present the EVEREST optimization flow with traffic prediction, which uses Python code and cloud FPGA architecture option. The Python function here, our neural network model, is with standard Python tooling exported to ONNX format, which is sort of standard for intermediate representation for machine learning models. Then EVEREST Python library support allows us to perform compilation of the kernel into the FPGA space, allowing us to play with parameterization for performance speedup and energy saving. The compilation also comes with the deploy script for FPGA Cloud, which is then executed by user to set a service. After the compilation, the architecture may look like this. Multiple neural network instances are on FPGA and auto-generated socket API interface so that a client application can use it with a standard network protocol. Some results here. Our baseline application was on regular CPU architecture was taking 5.5 seconds for 10,000 predictions on 10,000 models, while with the floating of 8 parallel instances of neural network, we achieved speed up of 24x, while also you cannot see it here, but we also achieved minus 75% of energy saving. So thank you for your attention, and I would like also to thank our partners in the project, which are IBM Zurich, Politecnico di Milano, TUD Dresden, IT4I Czech Republic, UZ Lugano, Vosis, Cmar, Tuferco, and Umtech.